Greetings! In this video, we are going to talk about the story of challenges in computer architecture. Von Neumann Architecture. This architecture, proposed by Mr. von Neumann, who was a Hungarian-American computer scientist at 1945. And roughly, nowadays, all of our computing systems follow this architecture. This architecture says that data is fetched from memory, it is processed by CPU, then it's written back to memory, and you can see that data is moving all the time between different components of the system. But what happens if one of these components, CPU or memory or input-output devices, are working slower than the other ones? So it changes to become our system's performance bottleneck. And it is mentioned that this problem can only be overcome through significant changes to computer or processor architectures, or rethinking the architecture. Moore's Law and its ending. Mr. Gordon Moore, who is the co-founder of Fairchild Semiconductor and Intel Corporations, in 1965 predicted that every year the number of components or transistors on an IC or processor will double for a decade. And after a decade, in 1975, he revisited his prediction and said that every 2 years the process will continue for next decade. But his prediction has been used in the industry for making a long time roadmap for setting goals for research and development, and it is called by people in research and industry a law, Moore's Law, but he never claimed that it's a law. And most of achievements in digital electronics are linked to this so-called law. Since 2010, some microprocessor architects report that the improvements are not following this law and they are slowed down. But however, in 2018, leading semiconductor manufacturers developed some IC fabrication processes which are claimed to keep pace with Moore's Law. However, this figure from Professor John Hennessy's presentation in ISCA conference shows that we are now in the post-Moore's Law era. But what happens in this era? In this era, we have to focus more on algorithms and software, or we have to focus on more specialized hardware, or we have to move beyond this technology. Silicon technology. You know that hardware is only part of this story, and for better performance, with better software and algorithms, we can still improve our computing systems performance. And without the ability to add more transistors, engineers or computer architects can work around the issue. They can work around the issue by utilizing more specialized chips like GPUs, like neural network accelerators, to complement the powerful CPUs. And there are other elements. There are other elements on this planet, and material scientists and mechanical engineers can bring about new innovations like graphene processors or quantum computing. Or they can, for example, work on quantum computing. They can work on graphene processors instead of working on silicon technology. Memory wall. Memory wall is in the growing disparity between the speed of CPUs and off-chip memories. From 1986 to 2000, CPUs speed improved annually by 55%, and off-chip memory speed improved only by 10%. So memory latency became an overwhelming bottleneck in computer performance, in computer architecture. And in this figure, you can see the difference, you can see the gap between processor memory performance. And here's a informative paragraph from Intel's report in 2005. Please pause the video and read it. It can be really informative for you, and it can give you a good view of what happened in computer architecture. So, what did architects do to address memory wall? They focused on architectural techniques. They focused on architectural techniques like caching, prefetching, multi-threading, new types of RAM, processing in memory. Caching is a mechanism that is going to gap the memory wall. It keeps data nearer to the processor, and when the processor needs this data, is going to access it faster than our RAMs can provide that data for the processor. And on prefetching, the architects developed a mechanism that is prefetching data before the CPU request. And multithreading is the mechanism that gives the illusion that we have more than one processor, than more than one core. It's better to say that it gives us the illusion that we have more than one core just by adding more resources to the pipeline of a core. And they proposed new types of RAM. You know that SDR reads only on the positive edges of clock, but DDR reads on the both negative and positive edges of working clock. And processing in memory is a mechanism that proposes, instead of keeping processing units only to CPU, it's better to have some processing units inside the memory, being able to do some computation inside of our memory systems, inside our RAMs, instead of moving everything to the CPU, processing them and moving it back to the memory. Dennard scaling and its breakdown. Dennard scaling, which is also known as MOSFET scaling, first it was posited in 1974 by Robert Dennard. It states that as transistors get smaller, their power density stays constant, so that the power use stays in proportion with area. And in every technology generation, according to the Moore's Law, every 2 years, if the transistor density doubles, the circuit becomes 40% faster, and power consumption with twice the number of transistors stays the same. In that time, computer architecture were playing with this formula. They were, in each generation, they were increasing the working frequency by decreasing the working voltage of processes. But as the dimensions of transistors shrinked, they were not able to decrease the working voltage because of reliability issues and current leakage. So the breakdown of Dennard scaling happened around 2005 to 2007, and the primary reason cited for this breakdown, as I mentioned earlier, at small sizes was current leakage, and current leakage poses greater challenges and also causes the chip to heat up. And this heat up creates a threat to thermal runaway, and therefore further increases energy costs. The further increases in energy is because of using special cooling systems that we need for dissipating the heat generated by processors or by ICs. And this figure shows how through years the technology shrinked, the dimensions of transistors get smaller and smaller, but on the other hand, the relative power per squared nanometer increased. So, what did the architects do this time when they saw the breakdown of Dennard scaling and they were unable to increase clock frequency to improve performance? They focused on multi-core processors. In this figure, here you can see a single processor with its resources for keeping CPU state, for interrupt logic, for cache and execution units. And here you can see multi-core processors, which a process incorporates several cores. And you can see here hyper-threading technology, which by adding more resources, architects try to address the memory wall challenge. And here, for further performance improvement, computer architects mixed multi-core technology with hyper-threading technology. And on multiprocessor is just putting alongside several processors. They can be single core or multi-core, and connecting them to a shared memory to be able to connect with each other, share data, and do and work on several tasks. And this is a image of a dual CPU motherboard which connects two processors with a shared memory, with shared RAM, with shared RAMs. And power wall challenge. This challenge is because of the end of Dennard scaling and the inability to decreasing supply voltage with new generations become of leakage because of current leakage in small dimensions and reliability issues. An increased core count in multicore benefits many workloads, but not all of them. But the increase in active switching elements from having multiple cores still results in increased overall power consumption and thus worsens CPU power dissipation issues. The end result is that only some fraction of an integrated circuit can actually be active at any given point in time without violating power constraints. So the remaining inactive area is referred here as dark silicon. And as we learned from previous lectures, Amdahl's law says that we cannot get linear performance improvement just by increasing the number of cores. And this comes back to the model thinking model that we have in building our computers. I mean, von Neumann. So what did architects do this time? They focused on and they proposed on-chip heterogeneity. This on-chip heterogeneity offers power efficiency. And on-chip heterogeneity can be categorized into three groups. The first one is single ISA heterogeneity, like what we have or what we see in ARM's big little architecture or in NVIDIA's Tegra 3 and Tegra 4 processors. The second one is multi-ISA heterogeneity, like integration of CPUs and GPUs on a single chip, for example, what we see in Sandy Bridge chips. And the third one is integration of specialized hardware processors, or SHPs. SHPs offer excellent power efficiency because they are built for doing a special task. They contain the circuits for doing that special task. So they are not doing extra work for doing what our general purpose processors do. Also, they can be powered off when they are not using, so they offer excellent power efficiency. And if you have any comments, any opinions, or if you have any questions, please write for me in the comment section of this video. And I appreciate your time and attention. Bye for now. I hope to see you in the next lectures.